Okay, welcome to my talk. I'm going to talk about asynchronous streams in direct style with and without macros. And so I'm an associate professor at KTH in Stockholm. And before going to academia, I actually worked at TypeSafe, which is now Lightbend. And I actually did my PhD here at EPFL, so it's nice to be back. So let's introduce today's topic with a simple task. Okay, so we're given an asynchronous method that returns the day of the year as a string wrapped in a future. Right, so day of year returns a future string, and it can return strings, you know, like 04/11 for April 11 and so on. And now sometimes this method can complete the future with an empty string or with null or nope. And what we should do is now we should create a future that's completed either with a string it's month, like it's April or whatever, where we turn the number into a textual representation, or it should complete it with not a date mate. Okay, so that shouldn't be too difficult. Also, we're in the expert track, so I'm sure you can come up with a program that does that. So we can, for example, use futures and for comprehensions to do that. First, we should actually define our regex here. And actually, I think regex are quite nice in Scala, so they're actually nicely integrated with extractors. So if you haven't used them before, give it a try. And actually, as a side note, since we're at EPFL, the regex support in the standard library actually originated as a student project that I supervised at EPFL a long time ago, so time frame 2007 or so. So basically, we have our regex here, and well, now we're just go ahead and say, well, when day of year completes, when that future is completed, we have a day string, and we can match on that string against our regex, extract the month. And what I didn't mention before is the other constraint is we need to use the name of month, and that's another method that returns a future. Okay, like imagine you're composing, you know, more complex things, and you have, you know, you call into services and whatnot. So then, you know, futures are really everywhere. So that's what we're trying to simulate. So name of month returns a future as well, and so that means since we need that result as well, we construct another future that, using another for comprehension, a nested for comprehension, which, you know, results in a future completed with the whatever the name is. Otherwise, if the string doesn't match our regex, we can create a future that's already completed. Yeah, so that's how we can do it. It takes a while to explain that. So the question is, can we improve readability a little bit? And of course, the answer is we can. And so this is one of the examples actually that we used before to introduce Scala Async. So Scala Async is essentially designed to simplify asynchronous programming, primarily based on futures, although, you know, there was some work and some ideas on how to make it more general. But in practice, people use it pretty much only with futures. Scala Async was created by Jason Zaug from Lightbend and myself, and we released that first in 2013. And it's actually a fairly popular project, so it is used also. By the way, who of you has used it before? Some people, not everyone. But we can use it to simplify things a little bit. So we can say, well, what we need to do is we need to create a future. So let's just create an async block, and within the async block, we can compute the result, right? And so it's similar to the future apply method, right? We can just sort of provide a body that computes the result. And so, all right, we do the same thing we did before with our regex, except that now, since we need the day of year, the result of that future, we call await. And what await does is it first checks if the future is completed. If it is, we can actually continue with our code. If day of year is not completed yet, the async block the body of the async block is suspended so that the underlying thread, which is normally a worker thread of a thread pool, that was executing the async block, the body of the async block, that thread now is freed again to execute other tasks that it should execute. Right? It's a pool thread, so it should really process all the tasks in the pool. And so that's what await does. It frees up the thread. And but it stores the execution state of this async block so that later on we can actually resume the async block exactly from that place, from the point where we called await. Right? And so this is what happens when the day of year future is completed. So await also registers a completion handler, which when the completion handler runs, then essentially we take the result of the future, the day of year future, and logically we replace the await call with that result and resume the execution. Right? So we resume here and do the match on the result. Right? And so this is what await does. And so we can really use await as a straightforward way to just suspend until we have the result, and we don't have to worry about the underlying thread being pinned because of that. Right? It's not happening. So it's a very friendly method to use. All right, and so also, I think what's interesting to point out in comparison to the previous solution, there's some interesting differences. So, for example, we don't have to name all the intermediate results. Okay, we all know naming is hard. So if you're forced to come up with names all the time, that's not ideal, right? Especially if it doesn't improve readability. So here, for example, we had to come up with a name for that result. We had to come up with a name for the response, and we had to come up with a name for this name here. And, we end up with these generic names that don't really help readability at all. So, like, if we can avoid that, that's good. So this is one advantage. Of course, we are free to introduce names as much as we want, but at least we're not forced to do that. Also, we don't need to explicitly construct completed futures. Okay, and I think this is actually important because it's the fact that we have to do this in the previous solution tells you that the fact that there's a flat map underneath actually kind of leaks to the surface, right? It's fine if you know that we're actually doing flat map and you know how to write the code explicitly using flat map. That's good, but certainly doesn't help clarity. Also, what's interesting is that the async block actually allocates fewer closures, right? So one async block is exactly one closure, right? So if you go back to the for comprehension code, since it desugars to map and flat map calls, we allocate more closures, right? For each call to map or flat map, we have another new closure that's allocated, and that's a performance hit, but also if we pass values into and out of closures, there's a lot of boxing going on often. So we can even avoid some of this boxing if we just make sure we just have one closure and all the shuffling of results and so on, it happens internally. So there can even be a performance improvement here. So it's actually rather nice. But let's do something more complex so that we test the limits here a little bit. And so how about instead of converting a single string, we need to consume a stream of multiple strings. And also, the output of our solution should actually be a publisher that produces multiple results. So it's not enough to just return a feature that eventually is completed. And so if you talk about streams, we should talk about reactive streams, or as they're also known as, which is Java util concurrent flow. Right, so since JDK9, these interfaces actually are now in this flow class, and so it's a small set of interfaces. Very few of them. The processor is not even essential, so we're actually talking about like 3 interfaces. And so what do they do? Well, I mean, they allow you to construct asynchronous streams, right? So producers, like publishers that publish events asynchronously, and subscribers that can subscribe to publishers to receive events asynchronously. And the subscription is also actually quite important because it allows the subscribers to control the flow of the events. And now this work didn't happen in a vacuum. There was actually some key prior work, and I think we should probably start by mentioning the observer design pattern. It's a classic gang of 4 pattern, right, where you have an observer and subject, a subject, and observers. And when this subject changes its state, say, we can have 0 or more observers notified, and probably the most important prior work here is actually the work on reactive extensions by Eric Meyer, where he essentially put the asynchronous streams on a solid foundation, right, by saying, well, what is actually an observable of T? Like, what does it mean in relation to other types that we know, like iterables, for example, right? And where he basically said, well, let's use functional programming concepts to provide ways to compose observables. So observable and publisher, I'm going to use those interchangeably quite often here, so bear with me. But so how to compose observables using higher order functions, right? And that's been really successful, right, with many implementations for various languages and so on. And then I think like the key innovation of reactive streams then is to have back pressure control, right? So that the subscribers are not just flooded with events from publishers, but they can actually tell via the subscription object, they can tell the publisher to say, well, I only want to receive at most 512 events or whatever, right? And sort of adjust the flow of events that way. So just to bring everyone on the same page, here's a quick run through these interfaces. So publisher is very simple, and I'm going to use the JDK 9 ones because those are this is what everyone's going to migrate to anyway. So the publisher has a subscribe method that takes a subscriber, and the subscriber needs to be able to receive events of type T because the publisher publishes events of type T. All right, and then the subscriber is essentially the interface that the publisher uses to publish events to each subscriber. So it has methods for each kind of event. The first event actually happens when there's a subscription from a subscriber, right? So when a subscriber subscribes to a publisher, the publisher, like in a successful case, creates a subscription object and calls the onSubscribe method, so that from then on, the subscriber can use that subscription object to control things. And then, following that, if the subscriber has expressed interest, that needs to be the case, right? Then the publisher can publish events and publish them to your subscribers using those methods. So if there's a next event of type T, we call onNext on each subscriber. If there's an error, if the publisher terminates with an error, the subscribers need to be notified of that as well. and the subscribers are also notified if the publisher terminates normally. Okay, and then finally the subscription interface that I mentioned, right, which has methods that should only be called by subscribers, and they can request a number of items from the publisher, right? They can say, I request 256 items, and then the publisher needs to adhere to the contract, which says, well, you cannot emit more than that, more than those events to the subscriber. And of course, we can cancel the subscription as well. Good. So now these are sort of the base interfaces here, and they are, of course, rather low level. So normally how people use these things is they use libraries that build on top of these interfaces. And one important such framework is this Reactive Extensions framework, right? So if you should know about that one if you know about streams, right? So it's the key is that we have a library that provides higher order functions to compose publishers. And I just wanted to give you a very short example, which is actually taken from the original article by Eric Meyer on Reactive Extensions. And so this is written in C#. But the idea is that we provide methods that construct publishers or subscribers, right? And and have higher order combinators. So, for example, text changes here is a method that creates a publisher that publishes in an event for each time the text in an input field changes, right? So each time I type in the input field, I make a change, there's a new event published with the current contents of the input field. And so that's the simple publisher of strings. And on that one I call select. And select actually would be called map. So in Rx Java, for example, it's called map, right? It's called select here because Reactive Extensions is integrated with link. And there, in link, the methods, the map is called select. So you can use comprehensions for that as well. So we call select, and what select does is it transforms the publisher into, or in this case an observable, transforms it to a new observable, such that for each word that's published by the first observable, we publish an event which is the completions for that word. Right? So imagine you have a search engine, you type a word, and then asynchronously there are completions being suggested to you. Right? And so that's what happens here. So that means for each event, for each word, the result of select publishes an observable. So completions actually is an observable itself, okay? So that means the result of select is actually an observable of observables. And, right, but select itself is just map, okay? But then we use switch, which is somewhat more complex, right? Where since we have a publisher or an observable of observables, what it does is it says, well, when you receive the first observable as an event, you start publishing its events. These are the red events initially. And as soon as you receive the next observable, you publish its events. So we switch to the yellow observable, because that's the next observable we have received. And these are the completions for the changed word. Right? So initially, we have a word in the text box, and we have completions, and then eventually the user types something, and then we receive an observable for the completions of the changed word. So that's the yellow events, right? And but the user can type again, so that means we may receive another observable for the completions for the next event. And of course, we have to switch always to the completions for the latest word. Okay, and this is what switch does. So as you can tell, you can actually build quite complex combinators here. Yeah, so this is how programs look like here. And so there are some challenges, obviously. One is we often need diagrams to understand what's going on, right? And so if you read the documentation for Reactive Extensions, you see a lot of so-called marble diagrams, which are an evolution of these of these event diagrams, right? They've sort of formalized the way how to present these things. And in fact, if you try to create combinators, these higher order combinators like select or switch or zip, what have you, this can be quite challenging, particularly if they're stateful. And the key here is that actually combinators that combine multiple observables, they are stateful internally, right? Even though the statefulness cannot be, there's no observable state, right? But internally, just to implement them, they're stateful. So if you're even just implementing zip, you've got to have state inside, okay? And that makes it somewhat challenging. And finally, of course, we have an inversion of control going on, which means we're actually building programs that, like, they're not running on the current thread. No, I mean, we're just building computations and they're like submitted for execution by the runtime, you know, using some schedulers and thread pools and so on. So the code we write is, of course, very different from sequential code that runs on the current thread. There's a very big difference, right, between these two things. So now that we know about streams, let's go back to our task at hand. So we're supposed to convert a stream of strings we want to create a publisher that consumes those events and produces a stream of results. Now, we want to try and do this like without the reactive extensions style, but instead the question is, can we do something similar to async await? Now, if we try to do this, we run into some issues, okay? First problem is trying to await events of publishers is actually not really possible because await takes futures as arguments. So we can't wait for the next event of a publisher, for example. So that doesn't work. Also, async creates only a future, so but we need to create a publisher that can yield multiple events. So that doesn't work, unfortunately. And so this is sort of one of the motivations for this proposal, which I call scala-async-flow now here, which is just saying, well, can we make Scala async a bit more general to support streams? And so the idea is that we extend async await such that we have a variant of async that can create publishers, right? It's not enough to just create a future. And so to distinguish that from the previous one, we call it rsync. And we also need to generalize await, so we need to be able to pass not just a future, but streams in there so that we can await the different stream events also. And finally, we need to be able to yield events. So we need to be able to yield the next event of the publisher, maybe yield an error, or yield done to indicate that the publisher has terminated. So first with the await, it's actually quite simple. So previously we had await and we pass in a future of t and the result is t. So I forgot to put in this picture which says, I can't believe it's not blocking, right? But so okay, but that's fine. The thing is we need to make this more general, right? So we need to say, well, this should be different, should not just be a future. So we need some kind of an object, it's like an async object. We need the notion of an async object, and which has a simple interface. So here I actually named it somehow, but it probably would be even better to have this as a structural notion to say, well, it needs to be an async object needs to provide these two methods, right? Where essentially we can query whether it's completed. Actually, I think the term completed is maybe not ideal, but because a stream in this case would complete many times. But we need this is analogous to future, okay? That's why it's called like that. But we need a method that says, do we have something to receive? Is there an event that we can get right now? And for a future, it's, is the future completed? And if so, please give me the try, so failure or success, right? For a stream, it would say, is the next event available? Yes or no, right? And by the way, so if it's available, we get the try. If it's not available, we get null. So it's either null or a try. And onComplete is, of course, analogous to the onComplete on futures, where it takes a handler from try of t to s and requires an execution context. And that's, of course, used so that we can say, well, we can register a completion handler that runs when the async object is completed, or when the async stream publish its next event, or when it terminates. All right. Now, once we've done this extension, right, we can actually formulate the solution quite simply by saying, well, let's use this rasync to create a publisher of string. So unfortunately, we had to provide a type argument here, but there are reasons for that. But okay, it's going to be a publisher of string, and now we can just wait. We can call a wait and provide the date stream. So that's the upstream publisher of date strings. I don't show this. I haven't shown the date stream, but it's it's just a publisher that pushes out date strings. And now the result of a wait is an option, because the stream could be terminated normally, in which case we get none as a result. Or we could have sum of x, where x is the next event published by the date stream. And by the way, if the date stream terminated with an exception, then the call to await throws that exception, right? So it's just like normal, what we would expect actually for that one, right? And so then we can check, okay, if the option, as long as the option is non-empty, we can access it and match it against our regex and yield whatever the next event is. Now, what's interesting? Oops, sorry about that. What's interesting is that inside here we actually call a wait with a method that returns a future, right? And this is actually interesting. Why? Well, because here we wait for a stream. This is a publisher. Right, publisher of string, but this is a future of string. So we need to be able to wait for different async objects. We can't just fix one of them, right? Would be too limited if you fix it to publisher in this case, right? So that's important. And yeah, and so then yield next, of course, we can call multiple times in a loop here, right? So once we've yielded the next event, we can go back and wait for the next event from the stream, and as long as that's non-empty, we continue. And finally, we do yield done. Okay. Now, how can we implement these things? Well, there are some alternatives, right? We can either extend the Scala async macro. That's certainly possible. We can try to put direct compiler support in there. And in fact, yesterday, Adrian Morris told me that there's a branch, that he created a branch which does that. So at least for the plain async await, so that's possible, of course. And we can build on top of continuations or fibers, and that's what I'm also going to show here. So let's start maybe with the interface, with the API, right? So rasync takes a body, and now this body, of course, well, we should have, so the body needs a context, which we call flow of t here. And the context is there because if we call await inside the rasync block, well, we need to know, we need to be in the context where we can do that, right? And also, if we want to yield an event, we need to be in the context where we can yield the event of the current publisher. And that's provided by this context, right? And so we use a contextual function to do that. And right, and the result will be a publisher of t. And so then await here, right, it'll have this async object as an argument, and it also needs a context, both a flow and it needs an execution context as well, because it'll register a completion handler, and for that one we have to say where it should run. So that's where we need the execution context. And yield next, well, that's super easy. We can use it inside when there's the context available here. And so then we can easily just yield the next event. So it's really kind of like the builder pattern that Martin showed in his keynote. So now the tricky bit, okay? How do we transform our async block? And I'm going to show you probably the simplest possible publisher, which in the end it's written in like excruciating detail on purpose. Okay, I've used the var on purpose, I've used the type annotation on purpose, and so on. So we're just to show, well, we have a local variable x that's reassignable, right? So initially it's none, but then later we're going to call await and assign the result to x. And then after the await, the only thing we do is we call get on x, right? That's like the simplest possible thing you can think of. It's like forwarding one event somehow. So what do we do? Well, we need to be able to suspend inside this async block, right? So, and the way the Scala async macro works, and this is very similar to how the C# compiler works, is it creates a state machine where this is a simple class, and that's essentially our closure, right? It's one class, and it has a state variable. So we number our states because we need to transition between states. And there's a result promise here. That's actually more like an implementation detail, but okay. And now the var x option of int, this used to be a local variable, now it's a field, right? It has to be a field because we're going to have to be able to access it in different states of the state machine, right? So we can't keep it as a local variable. And so the state machine, we can start it from the beginning, from state 0, okay? And we do this by calling apply. It takes a try. Initially, there's no try to provide, so we just provide null, essentially. And we start in state 0, and what we do is, well, we start the code from the beginning. What do we do in the beginning? We assign none to x. This is the initial code here, right? This is like the first thing we do. We assign none to x. Now you see why I have this excruciating detail, because this is some code we do, could be more complex, right? And the next thing we do, because the next thing we do is already calling await. That's the very next thing we do, right? We call await. So how does that work? Well, S is given, that's a publisher. We somehow need to find the corresponding subscription for that one, but we have a context flow, so we can look it up in the context. And the subscription, we can check if there is a next event there. So we call get completed. If it's null, it means there's no next event yet. So you've got to suspend. The only thing you can do is really suspend and register a completion handler. So we do that. But before we register the completion handler, we change state to 2 so that once we resume the state machine, we resume in state 2, right? And the completion handler basically says, oh, once I'm completed, I'm going to call the state machine with that event. So that's the try that's passed into the state machine. But this is going to happen. Apply is going to be called when state is 2. So that means when it completes, we call apply and we are in state 2. So that means in state 2, we have a try, right? And we can check if it's a failure or not. If it's a failure, we complete our promise with that failure. If not, we can get the result out of the try because it's a success. We can get it out and change state to 1, right? And 1 is the state where we run after the await. We resume after the await. So this case too is actually bookkeeping, right? This is happening when the thing is completed or we have the next event, right? And we do the bookkeeping to know what should happen next. What do we need to do? But the actual code that runs after the await is actually in state 1, right? So we change to state 1, call apply, which means we end up here. And the x.get is actually the entire piece of code that comes here. So of course it could be a complex expression. In this case, it's just x.get. So this is what we do here, and we complete the promise. Okay? So that's essentially how it works. I hope it made some sense. I don't have really time to go dive into more details. But so that's one way to do it, and the compiler can do it, a macro can do it. Well, macros maybe should not do it because they just become compiler phases that do it. So, but we can also think of running on a runtime system that provides a bit more support, like continuations. So, and that's what Project Loom in the OpenJDK does. And the idea is to provide features that we can use to build lightweight, high-throughput concurrency constructs. In particular, it provides delimited continuations and fibers. So fibers are essentially user mode threads, but they're interesting because of their integration with the JDK. But and this is, of course, still under active development, so you can't. There's no release that has that yet, but it's there's a lot of people now working on, so it looks quite promising. So how do these continuations look like? Well, the basic idea is that you can take a runnable and turn it into a continuation. So this is actually quite simple, right? You just provide a runnable, and in the body here, you can actually suspend and resume the continuation, right? Now the thing is, this is a super low-level API, clearly. Like, if you want to pass in values and out of the body, you need to build higher-level abstractions. That's not provided, right? So you need to do that yourself. So here's like the hello world example of continuations. Just very, very quickly run through it, but it's really simple. Like, you create a continuation, you call run. When you call run, you start it from the beginning, right? And it runs until either the end or until it suspends, which is done with yield, right? So you can yield the continuation, and that makes run so run completes, and okay, we can check whether the continuation is actually finished or not. In this case, it's not, so we set continue to true, and then we can resume the continuation by calling run again. So we resume by picking up from the yield point here and resume things. So that's very simple, and of course this makes it quite easy to implement this model, because in our async, essentially when we're given this body, we just need to create a continuation where our task evaluates body, and it can do that because the flow here, the delegate is actually in scope, so it works without any issues here, right? The body has access to the delegate, and everything works out fine. And inside the body, we could have invocations of yield or await, yeah. And I'm going to show you await too. But if it runs into completion, we can emit events, and or if there's an exception, we can catch it and so on. Await now is very simple too. Basically, we're given our context, and we can check whether we have something to consume. If it's null, then we don't, which means we need to register completion handler. The completion handler can resume the continuation, so the flow context provides a way to resume the corresponding continuation. And once the handler is registered, we can suspend. And of course, resumption will happen right after the suspend call. So it's at that point we can resume. Okay, so this is actually very simple, and there's even more. Like, we even wrote a paper about this. So you have 30-something pages of text, which actually has also formalization. So this is actually the first reduction semantics for observables. Before that, Eric Meyer and others did like a denotational semantics, but this is actually reduction semantics, so it's quite nice, and you can do type soundness proofs and protocol conformance, so that the publisher doesn't publish more events after it has terminated. For example, that's like an invariant that actually the type system provides. And we also talk a bit more about the macro-based implementation there. So there are some open issues that I should mention. So one is the red and blue functions issue, right? Where if you want to call a suspendable method, which in our case, it's methods that require the flow context. And that means this caller has to be suspendable too. So that means, particularly if I have a higher order function like map, it takes a function and assume I want the argument function to be possibly suspending. Well, then I need to prepare the map for that. I need a variant of map that allows me to suspend, that allows me to call a suspendable function. Right? So I need two variants for each of these higher order functions, right? So red and blue variants. So that's not good. And of course, monads suffer from the same issue. And so that's something to work on. Loom continuations themselves actually don't suffer from the problem. So we can actually suspend anywhere as long as there's an active continuation. And so this suggests that we may actually be able to relax the need for the flow capabilities, right? And so I think there's some promising work I think that's possible on like API design to do that. Yeah, so I'm gonna come to the end here. So we have some resources. So the prototype implementations, the two ones, one based on macros, one on the continuations, is on my GitHub, and you may want to look at the cont branch because, well, it uses Project Loom continuations, and it's actually also the only branch that actually makes use of Scala 3, so it's more interesting. And also here, I try to release preprints of things so that you're not behind paywalls always. And yeah, that's it. Thank you. Questions? There's a question over there. Is there a microphone? Okay, over there.
Thanks. It's really interesting what you're trying to do to bridge these two worlds. I'm wondering if you could show an example or explain how it would look for a little bit more complex example, like a flat map, concat, and with the buffer, and to sort of there's this imperative style, how it would work out in practice.
Yeah, so I mean, well, there are some more examples. In fact, so this paper I mentioned actually has a kind of an, I like it. I don't know maybe I can find it real quick. Hold on. See, I copied and pasted code here. So let me show you a bit more. In fact, if you have statefulness and things like that, it really becomes much easier to use direct style. Sorry. Yeah, so zip, for example. Zip is actually interesting. It's more complex than you think, right? You may think, oh, zip, that's easy. We just, well, in this case, it's a quite general zip method because it zips up a whole sequence of observables. So replace observable with publisher and you get the same picture. But the idea is we have just a rather general zip method. It takes the sequence of observables and the zipper is a function that combines the elements, combines the events of each observable. And so the result is observable of R. And so what we can do here is we need to keep track of a whole bunch of stuff. So in particular, we need to wait for the next event of each source, right? Oh, someone's calling. That's too bad. We'll have to delay that. So we create an array that can hold the next events. and we can actually just loop through and just wait for the events. And the cool thing is that this will not decrease performance, right? Because when we suspend on the first one, well, we can still the next producer can already produce the event that will be immediately available once we go to the next event, await call, and so on. So we can actually just collect these things and then decide, okay, what to do. Do we have you know, is it okay to run the combiner function and so on, right? So, you know, at some point these streams terminate, and they can terminate at different points. They maybe don't produce the same number of items either. We have to handle that. I mean, with direct style, it's rather trivial. If you can do sequential programming, you should be able to do this also, right? So I think it's, yeah, it's quite nice. So I encourage you to look at the article. And also, because there are some other examples as well. So there's like a challenge problem with a solution also here, where it's also a bit like combining different streams and have some statefulness in there as well. Actually with buffers and windowing also going on, right? So you can like, you can say, well, I have two streams, I combine them, but I need a window, right? And I need to reduce multiple events of one window and check conditions and what have you, right? And not always publish an event for each received event, no, but I have a condition that makes it much less regular and so on. So my advice is just to look at the examples in the paper also. Any other question?
Okay, so in your example, you have used a mutable variable with a while loop. My question is, would it be possible to rewrite this example using more like idiomatic functional style with maybe a for comprehension or tail recursive function?
Are you talking about this one or?
Yes.
Okay. Yeah, I mean, there's nothing that prevents you from just using combinators to combine publishers too, right? So I think that, I mean, this is maybe not like the best example. The example, what this shows here is that it's very simple to go from a future-based code to stream-based code, right? Like this looks very similar to the initial future-based async await usage, right? But, I mean, I agree with you that I think this is like a very regular example, so it's not so difficult. So sure, you can just use map on a publisher or whatever, and it will work the same way. So, like, you're not forced to write it in this way, but you can.
Well, we are already out of time.
Okay.
So, thank you.
Thank you.